Awesome. So, at some point in the afternoon on Monday, the various supplications being made to the various deities of all of the people at this university were answered, and the strike has been avoided. A tentative agreement has been found between the union and the university. All that remains is that the union now votes on the ratification of this deal. So, there's not going to be a strike on Friday like everybody thought that there was going to be for quite some time, including myself. If anybody has sort of made plans based on the strike happening because I was fairly certain that the strike would be happening, then I apologize for that. But we must continue on. We must accomplish our course in due course, so to speak. So there will be no interruption to classes. There will be no interruption to assignment deadlines. Everything will proceed according to the schedule as originally laid out in the course syllabus. Praise be. So yeah, I guess they didn't really want the strike after all. But any questions about that? Okay, so we have a fairly chunky subject to get through today. We're going to be talking about strings, string formatting, and file input and output. Normally, it's kind of interesting, right? Like, normally file I/O is something that you cover earlier on in a programming course, but just sort of out of happenstance, when you took 1MD3, it kind of required you to have some knowledge of classes in Python in order to understand how file I/O was working. And in C, it requires you to have some knowledge of pointers in order to understand what's going on with file I/O. So we kind of find ourselves in a similar situation to 1MD3 for once, where file I/O is coming after the majority of the topics in the course have been covered. Once we have covered this, we only have one major topic in C programming remaining, which is that of data structures, or the struct construct itself. Just a quick intro to that if you're sort of working ahead on assignment 2, which I highly encourage. Structure is simply a way of packaging up several variables under one common name. It technically creates a new compound data type. It's somewhat similar to the way that Python collects multiple attributes into a class. However, it is not a class. It lacks the ability to bind functions specifically together to create something that we would recognize as an object. You simply have the ability to collect up a bunch of variables, give it a name, and work with it. Get the particular elements out of it via dot syntax, the way that you might expect it to work if it were a class. At any rate, that's not today's topic. Today's topic, we're going to be talking about strings and formatting and file input, output. So, good. So let's just quickly recap characters and strings. Recall that in C, double quotes means that you're working with a string, and single quotes means that you're working with a character. In C, strings are encoded as character arrays, which are null terminated. So, if we declare foo, the character array, as value bar, in memory, this will be written as BAR null character. You don't have to worry about allocating space for the null character. If you allow the character array to decide for itself how big it should be, it will include the null character by default. However, if you're manually allocating the size of the character array, you must always leave space for the null terminating character. And the reason for that will become rapidly apparent as we go through the string libraries. Essentially, most of the useful functions in the string library expect your character arrays to be null terminated. They use the null terminating character as an end condition for whichever operation they're performing. So, if that end character is missing, in typical C fashion, it will just continue to gobble up all kinds of unallocated garbage memory, and all the way until it reaches either a naturally occurring 0, which, to be fair, is reasonably frequent, or it might just exceed the bounds of your allocated memory space and cause you a segmentation fault. Neither of those situations is desirable, though one is eminently more desirable than the other. Neither is good. At any rate, remember, all strings are arrays of characters which have a bit width of 1 byte. Strings are delimited with double quotes, characters are delimited with single quotes. Any questions so far? That should all be reviewed. So, the importance of null termination. I have a terrible habit of giving you the next slide while I'm on the previous. I apologize for that. The null character has a very important function in C. You may notice that C does not know when an array ends, although it always knows when one begins. Why does it always know when one begins? Yes?
Just of the array?
Yes, the array identifier itself is a pointer to the first memory cell where the array starts. So you always know what the start position of an array is, but you never know what the end position of an array is unless that has been passed explicitly. The null character, which is written as an escaped 0, not O0, is used to indicate the end of a string in all standard library functions. And if the standard library does it that way, you should do it that way too. But using the fact of null termination in your own code is also a very good idea. Since everybody is assuming that strings end with null characters, that is an assumption that you can build into your code as well, and it's a valid assumption. A common pitfall is not allocating enough space in your character array for the null character. If a string is missing its null character, the functions in the standard library will continue operating into memory space not allocated to the character array. This could introduce smelly garbage or even segmentation faults. So, we're going to talk about how to convert numbers to and from strings over these next few slides. So, in Python, this is relatively easy. In order to convert a string to a number, all you do is you call the integer function on that string. It'll spit out a number if it's convertible to a number, and an exception otherwise. In C, things are slightly more difficult, just like everything. So, double, by the way, what is a double?
64-bit.
Yes, 64 bits of what, though? This refers to a particular type of data. What type of data are we referring to? Floating point, that's right. So it's a double precision floating point number. So, the C standard library, stdlib.h, defines str2d, string to double, which converts decimal numbers into double precision floating point numbers, or doubles. So, returns a double, takes constant character array string, takes a double pointer, end pointer. So, we'll get to this. First, string, str, is a pointer to the string that you want to convert. Leaving white space will be ignored. However, if you have characters other than alphanumeric, or If you have characters other than numeric characters, this will possibly fail. str2d converts as much of the string as it can into a double, and then returns that double. So it will consume the string until it hits a character that no longer constitutes a valid double. Basically, it'll read it so far as the number is in the string, then it'll stop. End pointer is the address where str2d stores the address of the character that it stopped on. So this is why it's a double pointer. Have we seen many double pointers yet in class?
It was in number 6 on our assignment.
Yeah, good. So the purpose of a double pointer in the context of a function call is so that you can pass a pointer by reference, right? So essentially, if you look at this function, it's already got a return value, double, right? Which makes sense. You want the main return value to be the number that you're trying to extract from the string. That makes a great deal of sense. However, for the purposes of further string parsing, it is useful for this function to tell you how far it got along in the string before it stopped. That way, you might be able to pick that up again, convert a few, maybe, just picking a completely random example that has nothing to do with any kind of assignment question that you might be having upcoming. Let's say we had a string that looked something like 73 minus 207. Let's just say we have a string like that, right? And also these are space characters. That's like normal for space characters. So we have, let's say, str, right? That will be pointing to the 7th character, right? Let's imagine this as like, let's just block this out so that's a little more explicit. I'm not going to do the single quotes, because holy hell. Right. So that's our string, right? I know we're talking about string to get to double at the moment, but we are going to have a string to integer conversion function that will appear very quickly in these slides. So, don't worry that these are not doubles. It's okay. We'll get there. So we have a pointer which indicates this 7, right? We will want to have another, let's say, current position, right? We have a current position pointer that currently points to nothing, points to null pointer, right? Calling a conversion function on a string such as this, okay. Let's say, for example, since this is integers, let's just use the correct, So the correct one is str2L, L for long, but it converts long integers for historical reasons that we'll get into, but So let's imagine that we are running str2L, right? So we're expecting the numeric value of this portion of the string to be the return value of str2L, right? what it does in the meantime, we give it this string pointer as its first argument, right? First argument. We give it this current position pointer as its second argument. str2l will read as far as its numbers into the string. So in this case, it will read these two numbers, right? It will compute what the numeric value of these is, so your return value will be 73 as an integer, long integer, technically speaking, and then str2l will place inside of current position the next character after it finishes its conversion, right? So current position will be returned as the first character after the number has ended, right? So if this is, address, 0 for, I should do that in a different number, they're a different color. If it's address 0, these are bits actually, but that's okay. 8, no. Is it? Whatever. What am I doing? I'll just do it in decimal. Whatever. What the hell? Right? So this will be given value 8 by string 2l. Right? So the question then, how is this useful? In this particular context, there are a couple of ways of dealing with white space. You can either pre-process the string to remove any white space that might be in the string prior to passing it down further down the algorithm, or you can simply ignore white space as you're going through it. But you would then write some portion of the algorithm which detects an operator, essentially. So it's kind of like, you have space. If you have a space, skip it. And if you have an operator, read what the operator is supposed to be, probably with an if statement, record that somewhere, and then once you have acquired an operator, under the assumption that only one operator will occur in the expression, which of course in the case of your assignment is correct, you can then move this pointer to a third position after the operator has been read, right? Because these guys ignore leaving white space, right? So then you come up with a second call to str2l. In this case, however, the start point in the string will be what? The current position, which we are now overwriting to become 16, right? In the previous step, yes?
What is the syntax of current position? Is that your double pointer?
So within the context of the calling function, let's say it's main, this will be a single pointer. It becomes...
Single star, whatever you want to call it.
Right.
Okay.
But you're passing it here by reference. So, in terms of syntax, the first call, let's actually spell it out, will be str, comma, address of current position.
Right, you want its address, okay.
Right. That pops it out one more level, right? You're passing that pointer by reference. Only rarely, only in very specific rare circumstances does this mean that you declare this as a double pointer in the calling function. Normally, this means you're simply including the address of operator at the time of the function call. Does that make sense? To some degree? It makes it easier, right? Like you could declare this as a double pointer inside the calling function. It's possible to do so, but then you would have to, anytime you were interested in doing anything with it at all, you would either be, dereferencing it once or twice depending on like what the circumstance is, and it's just easier to keep it at like, a level 1 pointer to deal with because it's just more understandable. Once it's here, right, and once you give this this function the address, then you're going to have to deal with the fact that it's a double pointer and dereference it either once or twice depending on the situation, right? Again, because pointers, if you dereference a double pointer once, that allows you to modify the pointer. If you dereference the value twice, then that allows you to reference the value indicated by the pointer.
Dereferencing twice.
Yes.
But so what's the syntax of dereference twice? Just write it without the stars.
No, dereferencing twice is 2 stars. Right? So if I have, so in the context of this calling function, right? So memory, right? Let's say we have a stack frame for main, right? Main has current position, which is a pointer to another, current position will contain a pointer to some other memory cell, right? What happens when we create the double pointer is, let's just say we have str to L, right, inside there. What's the name that we give that? End pointer? End pointer. End pointer is given the address of this guy, right? So that's a terrible arrow. That's a slightly improved arrow. Right? So, inside of str2L, you dereference this guy once, you get this value here. Right? You dereference it twice, you get this value here. Right?
Yeah.
That makes sense?
I just don't know the syntax.
Right. So, end pointer 1 star, that's dereferencing once,
Okay.
right? Double star, dereference twice. Think of the star as an operator, similar to like negation in arithmetic. It's a prefix operator. So you can use, like, in the same way that, negative 1 is just 1, because you apply the negative once and then you apply it again. The same thing happens here, except it doesn't cancel out. Questions, sir?
Do you need long int in front of the str2L?
In this case, it is correct for you to understand that this function is returning a long integer, not a standard integer. So in this case, that means a 64-bit integer rather than a 32-bit integer. It is perfectly possible, if you want to squeeze this inside of the size of a regular integer, for you to cast this as a regular integer. However, that is one additional step that you have to do.
I meant like syntax-wise, do you need to write long int in front of that?
No, this is just telling you the return type. This is the function prototype.
Okay.
Yeah. No, so long as it would be something like x is equal to str to L ... right? Where x is like long int x, right? Declared that way. Or alternatively, you could also do it int x, x is equal to cast as integer str to l dot dot dot, etc. Right? We talked about casting, right? Yeah. Casting, as review, casting is a way of coercing a value to acquire a different data type. It's not quite the same thing as type conversion in the Python sense. Type conversion in the Python sense will, for example, convert characters to their corresponding values as indicated by the character. Casting a character as an integer in C will give you that character's ordinal value, the actual ASCII code, rather than the face value of the character. That way, any character can be converted, not just ones that are sort of valid numbers. Make sense? Any questions? C is a complicated language, eh?
I like it. Better than Java.
Better than Java?
Yeah, Java is just like the syntax is just weird.
Okay, so I know that C is like a, this is harder than Python, and I know, fortunately Java is dying, so, in 20 years nobody will even remember that it exists. But,
Minecraft. Minecraft.
They're changing it over to C.
What?
C++. I think they're changing it over to C++. Well, because Microsoft bought Minecraft and they
Yeah.
use C++.
Well, that's C++ is Bedrock Edition. I don't think I'll replace Java.
I
mean,
think they're trying to.
Can you imagine how much better it would run if it was not Java?
It's also the problem where right now they have two completely separate engineering teams on Minecraft.
Yeah.
They have to communicate.
They shouldn't do it in C++, they should do it in Rust, but anyway.
Modding C work.
We're getting off topic. So the nice thing about C is that, there's a reason that this is only a half course on C, right? You can learn everything you need to know about. Once you've got the feel for this type of operation on pointers, C will not really present any, it's like, once you've got this and structures, C presents no, new basic constructs past that. We will be able to sort of exhaustively cover the C programming language in this class. By the time this class is finished, you'll have seen everything. There will always...
Seen everything?
Ha! I mean, if I stopped to waggle my eyebrows every time I uttered that phoneme in this class, can you imagine? The one thing we can't obviously cover exhaustively is all of the material in the standard libraries, right? That's also subject to development and change, right? That's, knowing how to use the standard libraries is very good, but, in terms of basic language constructs, you're not going to, once we've done structures, you'll know everything that there is to know about C, which is kind of why C++ exists, right? Once you know C, C++ can be layered on top of it. I'm sure I've mentioned this before, but all C programs are valid C++ programs, right? So, to learn C++, it's useful to know C because you can fall back into a language that you know how to use and then, use the C++ constructs as appropriate. Man, I've been talking about, all right. Anyway, so let me just, let's go through this then, now that we've done the example on the board. So, str is a pointer to the string to be converted. Leaving white space will be ignored. str2d converts as much of the string as it can into double format and then returns that double as the standard return value of the function. The purpose of the return by reference here is to be able to return two values from a function. In Python, the way you do that is you just return a tuple that contains both the things that you want to return. In C, you have the regular return value, and you have anything passed by reference is an implicit return value. And this is often, like you're going to see this quite a bit as we go through some of these standard library functions. End pointer is the address where str2d stores the address of the character that it stopped on. This is an example of a function using pointers to, in effect, return two values. There you go. Here is an example of syntax. 51.2% are admitted. We have the string, we have a string pointer, which is, in this example, the equivalent of our current position pointer. Double D is equal to str2d string address of string pointer. Note that this is a level 1 pointer, and we take the address of that level 1 pointer, pass that to the function. And then you can see that we are using the double that we are creating here, using the F format tag, which designates this as a floating point number, and in the output, you can see it's printing it to 2 decimal places. We're going to be covering this type of thing later on today, but point 2 means a floating point number that you are displaying 2 decimal places of. This is, it's kind of, there's no like actual arithmetic going on here, so that you can see that like the double is just a regular floating point number, just like anything else. We could add like 0.5, like 5.7 and get the arithmetic to show here, but at this point, this should be convincing enough to you that this is not a string. The format tag S is designates printing a string. Question?
Did you do like 0.0 to just get the whole number at the front?
Say that again,
Can you do like 0.0 to just get the number at the front, like before the decimal?
Oh, that's an interesting question. I don't know. We're going to be talking about format tags later on, so hold your question for then, and we'll talk about it then. Okay? I've already been jumping around too much. I'm going to get more. This is an important point right here that's partially cut off. If this function fails, it will return a 0. Now, you might say to yourself, well, that might be a problem, because how do I tell a 0 from a valid 0? And the answer is, you examine the end pointer that it returns to you to see if it's the same as the pointer that you put in. If it fails to convert anything, then it will say that it stopped on the same character it started on. And that's how you tell if this is valid. Because there's really no valid thing it can return to indicate failure. And because C doesn't have exception handling, this is the type of thing that you have to do. You have to check for these sorts of things manually. Any questions? Yes?
How do you check it? Like you check where is the value at 0 and see if it matches string pointer at 0?
If string pointer is equal to string, no dereferencing.
Okay.
Right? Because then you're checking to see if these guys have the same address. Make sense?
Mm-hmm.
These are really good questions, by the way. I'm really encouraged that you guys are like pushing on these types of nuts and bolts problems, because that's precisely what you guys need to know for the assignments. It indicates to me that you're taking the class seriously, which I appreciate, because holy hell, like I have had classes where nobody in the class is taking the class seriously, and it's really not much fun to teach. Last semester's on MD3. The summer semester, not the winter semester. I know some of you from the winter semester, but anyway, so converting strings to integers. Very, very similar procedure. The function works almost precisely the same as the string to double. One difference, we have a base indicator. So the base accepts the base is the let me start that sentence over. Integer base, this argument here, is the base of the number that you want to read. This allows str2l to convert not just regular decimal numbers, but you can also convert hexadecimals, octals, anything you like, right? You can actually indicate any number between 2 and 32. So if you wanted to do like base 5 arithmetic or something like that, it all depends on how your string is oriented. Incidentally, this is why when in 1MD3 where I have that one question that asks you to do like a base like 48 number conversion or something like that. The reason I picked 48 or that type of number is because it's higher than 32, because Python in the back end is using this function as well. So Python, you can indicate any base between 2 and 32, and it'll perform that conversion for you. It just sort of steps into the appropriate number of alphabetic characters. But anyway, so if you have, for example, a printed pointer that has been printed using hexadecimal characters, or any hexadecimal number that you're trying to read, you indicate what here? For hexadecimal?
16.
16. Very good. Octal?
8.
8. Good. If you do this, it'll, if you do 0, it'll try to figure it out itself, but I always recommend telling it explicitly. Any questions? Good. So, there are, in fact, a number of conversion functions that work in a very similar manner. We've got doubles, floats, long ints, unsigned long ints, long ints, and unsigned long ints. With appropriate, you can see these roughly kind of follow the sort of naming convention you would expect. So, note the absence of functions converting shorts and regular integers. This is possible directly using the unsafe A to I function. That's ASCII to integer. A to I is unnecessary, as string to L can be easily typecast as either int or short. In general, do not use A to I. I know that if you're looking on certain websites of questionable repute, and I sometimes include Stack Overflow in that, they may recommend for you to use A to I for integer conversion. I'm going to say right now, it's not safe. There are some functions which are included in the C standard libraries for historical reasons. Very, very old code in the Linux kernel may use A to I in a safe way. But in general, when I say don't use a function, don't use the function. Okay? I will, if I catch you doing something like that, you will be punished. You will have to write out 1,000 lines. I will use the correct standard library files. Yes?
What happens when you pass a long int into a short one, but the value is too great for the short int?
It'll just chop off anything that's in the upper half. Yes?
Isn't A to I what we just had to use in our lab though for doing
We did.
this?
Oh.
Yeah, we did. I didn't even know what it was. I was so confused.
Hmm.
Yeah,
But I
let's give
learned
it
it
an
again.
example function.
Which lab was that?
Yes, sir.
Seven.
Mondays.
Hmm. Is that the one where you're doing the testing? Or
Make files.
It was make files.
Make files.
What are you doing?
so I'm going to confess something here to all of you right now. I didn't write all of the code in all of the labs. This course, I constructed it I constructed this course last year from sort of several predecessor courses that had been taught the previous winter by a professor who focused way more on the C element and then tried to cram all the Unix stuff in at the end, which I think is a very poor way to actually learn any Unix stuff. It's like best done in tandem, which the powers that be in the department, I checked with them how they wanted the course laid out, and they agreed that it should be a week of this and a week of that. So some of the lab material is inherited. I didn't create all of it myself, and A2I is still unsafe, even if previous professors from teaching this course have used it. So please use str2l. I will open an issue report on my GitHub for the course materials to fix that. But yes.
Was that old course what 1AX do?
Yes. So 1XA3, which formerly was taught by Curtis Dalvis, who's you guys probably have seen him in 1JC3. I would imagine he's taught that for like forever. Yes, it was a different course back then. In 1XA3, there was no C programming whatsoever. The second half of the course got into internet stuff and doing some light databasing and that sort of thing, which, as I understand it, has now been moved to 1XD3 or possibly into 2XA, 2XC. It's been moved into some other experiential course other than 1XC3. That was the part that was removed to add in the C programming, which actually I think originated in a second year course. So we're bringing it into first year because in the second year there is 2GA3, which is an architecture course, which cavalierly assumes you already know how to do C programming. So it's good, for prerequisite reasons, it's necessary for you guys to know some C programming before you take an architecture course, which of course makes a lot of sense because if you don't understand C, there's no way for you to be able to understand computer architecture because C is computer architecture to an extent. But does that answer your question? Yeah. Any other questions? Yeah. Good. Now that we know how to read numeric values from strings, the question remains, how do we write numeric values into strings? Ha! Trick question. We've been doing this whole time. Printf writes to standard output, but Scanf writes to a specified memory address. So you can use all of the regular way that you would regularly print something using printf. However, rather than target standard output, you target a specified memory cell, that is to say a declared character array, and then it will print stuff into memory rather than to the screen. There's actually a whole family of printf functions that write various things to various places, as we're going to see. The difference with and printf is it requires a couple of different arguments. First, it requires the pointer to the memory cell, to the beginning of the string that you want to write into. Then, it requires a size. So it requires you to tell it the maximum size of the string that it's writing. This way, you can avoid problems with, like writing too much into the memory cell. This is actually, so Sn_printf is like string numeric printf, where n is this size. So there's a version of printf called sprintf, which does not do the size checking. that is considered far less safe than Sn Printf, which does check for its own bounds. This is like one of the rare exceptions where C is actually doing some work to ensure it's not violating its own memory space, so I highly recommend you take advantage of that where available. So, str is a pointer to the memory address the characters will be written to. Size sets a maximum number of characters to write. Remember to leave enough space in both of the above for null termination. Every argument passed the second is used precisely the same as printf. So past this point, everything subsequent to that is exactly as you know from printf already. Any questions? Yes?
Why is it size T in size?
This is a type definition that exists inside of, the standard library. It's defined inside of the standard library. Essentially, there are limits placed on the size that a character can be in the form of how many bits are allocated to the number that represents the size of an array. This is a system value and will vary by system. That's why it's not like defined as an integer or something. But this is also true of things like integers, like what an integer constitutes is dependent on the operating system, right? It's defined in the standard library files. So, you shouldn't worry too much about that. It's just like, however much it is, you can assume that it's an integer value regardless as to what the bit width representation is. Does that make sense? Good. Any other questions? Okay. So, the return value of Sn Printf is the size of the format string after substitution. So this is the number of characters that get written into memory. Note that this may be distinct from the size of the string written into memory. So if the size of the string that you're trying to write is less than the available size, then the return value will be the same size as the number of characters you're trying to write. If the string had to be truncated or cut off in order to fit inside of the available memory, you will have a mismatch between the return value of Sn Printf and the number of characters that it's trying to write. So this means that we can check to see if the string had to be truncated by comparing the input size to the output size. So if we have a couple of, so we have I as being 1337, size, this complicated mathematical expression, which indicates the number of characters that should, like this is, like log base 10 tells you how many digits, basically, right? You add 1 to that, take the ceiling of that, because this will be a floating point number, right? Because it's a log, the log output will be floating point. Ceiling, simply take, like it always rounds up, right? So then convert that to an integer, that will be your size. We set a buffer, allocate size times the size of char, right? Then Sn Printf into the buffer that we've decided, the size that we've given, write it as an integer, right? And then, if the return value here is greater than the size, then the write operation was truncated. It shouldn't be in this case because we did some careful math in order to determine what the size of the integer should be. But, if you're sort of cavalierly not calculating the size of the character array that you're wanting to write into and just sort of saying, it's probably less than 100, and you just get 100, which incidentally is a technique that's often used for taking input from users. then, you're much more likely to run into a problem here. If we didn't have the +1, we might hit this every time because we would be truncating the last character of the paper, putting the null terminating character in. Make sense? Sort of? Any questions? So we've talked about conversion, and that took, like, these 7 slides took the first hour, so, uh-oh. So let's talk about string manipulation. Let's talk about string copy. Have you ever wanted to copy a string? Well, now you can. String copy is a function which copies one string into another, right? So we've got 2 versions of this function, following the same pattern with sprintf and snprintf. The presence of the n indicates you can give it a size, and it will not copy anything past the size indicated. This is a safety precaution. So, very simple. Take both of these, take the string stored in S2 and copy it into S1. So it's take this, copy it there. You know which one of these is the one that's being read by the fact that it's declared constant. Right? So, string n copy will, the extra argument in string n copy is similar to size in snprintf. String n copy will copy at most n characters. This guards against buffer overflow, making string n copy the safe version of string copy. Buffer overflow in the stack smashing example sense that we have talked about previously. Once again, you must make sure that S1 is large enough to contain S2 and that n takes null termination into account. String cat. String cat, so cat stands for concatenation. Can anybody tell me what concatenation is?
Adding something to the end.
Yes, you run them together, form one from the two. So, string cat usage is similar to string copy. The null character terminating S1, the null terminating character in S1 is overwritten with the first character of S2. So, essentially, S1 has to be a character array in which more space has been allocated than is currently being used. So the null terminating character will occur somewhere in the middle of the string. Can I erase this? Yeah, okay. Oh, yeah, sure, go. I'll use this board. So, basically, if you have some amount of memory which has been declared, let's say you have some string which is occupying the first piece of this, then if you're concatenating it with this guy, then what will happen, the concatenation process, is this value gets overwritten with the first element here, it writes them in, puts the terminating character in, and there you have it. String concatenation. Question?
So does the first string have to have enough memory allocated for the concatenation?
Yes. S1 must have enough memory allocated in order to accommodate the size of the string after concatenation. Yes. Yeah. So. Good. String length accepts a string and produces the number of characters in it, null character excluded. So we have a length function here because the null terminating character is a way that we can algorithmically determine what the size of the thing is, right? So this is a function that does that. Just very simple. It's just a counter in a loop that's waiting for the null character to occur and then returning however much that counter got up to, right? This is slightly smaller than it should be. I know I'm throwing a lot of functions at you, but you know, it's kind of the nature of things. So, string comparison. Sometimes you might want to check to see if two strings are the same string. In Python, this is very easy. All you have to do is use the equality operator, the double equal sign operator. In C, that doesn't make any sense because the strings are pointers, and unless they are the same pointer, they're obviously not going to be the same, right? So an equality operation over two string names will default to checking to see if the pointers are the same, right? However, to actually check to see if the sort of face values of the characters in the strings are the same or not, we use string comparison or string n comparison with the same distinction as every other time we've seen the n in there. So, inputs are the same as previously. These guys compare each character in the string sequentially, returns 0 if the strings are the same, a value less than 0 if S1 is less than S2, and a value greater than 0 if S1 is greater than S2. In this context, strings are ordered by the ASCII values of their characters using alphabetization rules. So basically, it's not comparing characters, it's comparing ASCII codes, right? So if the ASCII code is less than, you know, if we're on character 7 and the ASCII code in S2 is less than the ASCII code in S1, then we are in this situation, right? This is also known as lexographic ordering. So if you're just considering alphabetic characters, ASCII has been designed so that if you were to take a bunch of strings and sort of sort them by the orderedness as given by string comparison, what you would get as a result is dictionary ordering. Right? Make sense? Question?
Can you just repeat what you said?
Yes.
Sorry.
So, let's imagine that you have an array of character pointers that are all pointing to their own strings, right? If you wanted to sort that array of pointers by the ordering that this guy gives over the strings they point to, right? What you would end up with is dictionary ordering, so lexographic ordering. If they were just words, using alphabet characters, the ordering that this would produce is the same as if you were to look them up in the dictionary.
Oh, I understand.
Yeah. Good. This might be useful to you. A table of rough equivalents in Python to the various C string operations we've talked about so far, and a couple that we haven't talked about. So str to L is the same as integer conversion, roughly. Sn printf is roughly equivalent to string conversion. String copy is roughly equivalent to Python's deep copy operation, which, of course, breaks aliasing. Like in Python, if you assign one string to another, all you get is like an alias, which is to say you're copying the pointer, not the actual memory. In Python, if you want to copy the actual memory, this is how you do it. And that, you know, string, this guy is calling this guy. This is basically, another way of viewing this table is Python functions and the C functions they're running behind the scenes. So if you have foo plus bar, that's string concatenation in C. Length of foo is string length. Double equals, less than, greater than, etc. is running string comparison in the background. Foo.index bar is strchr, or string character. And foo.split bar, string token. So tokenizing. Tokenizing is another, if I may say so, valid approach to the numeric problem that I've given you guys. I'm not going to cover string token in a huge amount of depth in the slides, and we don't have a lot of time for it anyway, but essentially, Geeks for Geeks has a good tutorial. So, surely this is generalizable. Given that in C, data types as a concept are somewhat ephemeral, it should be the case that the above operations on character arrays should be reasonably generalizable to arrays of other sizes, or arrays whose members are of different sizes, shall we say. So, string.h contains a set of memory operations which are highly similar to the operations on strings previously discussed. So, rather than accepting and returning character pointers, these functions use void pointers, meaning that these void pointers can be cast to any data type or any bit width by casting it to the appropriate data type. So we've got mem copy, which is equivalent to string copy. We've got mem comparison, equivalent to string comparison. We've got mem character, or I'm not sure that stands for character actually. Mem chr equivalent to string chr. And there are more besides. I can't cover all of them, unfortunately, in this lecture. Yes?
For the compare one, what size of the memory is it comparing? Or is it just like every bit?
Well, if you use mem_n compare, then you can set how much memory it's comparing, which is recommended. Any other questions? So, I'm hoping that, like, through my talking about all of these at this, with this degree of length, that you guys can start to sort of abstract out and understand the general principles at play here, and understand that these are generally applicable to pretty much anything in the string library, or standard lib as well for these types of functions. So, you know, the question that you should be asking is, so if these are integer arrays, how does it know how to stop? If you're thinking that way, then you're thinking like a C programmer. Good. So, moving swiftly on, let's talk about string formatting. So, up to this point, we have only briefly touched on the advanced features of the string formatting tag %. We will now get into some of the more advanced features. I'll just preface all of this by saying that there's a question on your assignment that's not the one where you have to compute simple expressions, the one that involves dates. How many of you have actually looked at assignment 2 so far? Cue Price is Right, losing music. Anyway, so I'll just tell you. There's another question on that assignment about date conversion, right? So you have to take like dates in like one format and convert it to another format and then back again by like, you know, reading out the integers, storing them, and then regenerating, you know. I remember like a previous time I set that question before students, and I had a student who basically came to me in the throes of final desperation and frustration with the code that they'd written because they had no idea where they were going wrong with it. And I looked at it and like, you know, coming into this, I was full in the knowledge that with the material contained in this section, that algorithm is about 8 lines of code, right? This person had written 150.
Oh my gosh.
Right? Yeah. So the moral of the story is, while it is possible to do everything with if statements and while loops, you can save yourself a lot of time and hassle by learning how to use the tools that you have available, one of which is the string formatting tags, right? Because you can use, like, these are used not just for printing stuff, but also for reading stuff, right? I'm not even that distressed that the person spent so much time on that when they could have just used formatting tags if they learned how much easier it is to use formatting tags. If you learn that as a lesson, then that's a good lesson to have learned from that type of an exercise. But of course, you know, general points on programming, the longer your program is, the more likely it contains errors. That's just math, right? So if you're having a very hard time writing a very long program, it is possible that you're having that terrible time because what you're doing is reproducing standard library functions that you could actually just be using, have much more reliable code, and you know, it's like, but I didn't want to learn how to do it, so I just used the if statements, and it's like, yeah, okay, you know, I do get it, right? Like, it's like you guys should all be to the point where you can fall back on self-implementation, right? Like, I'm not expecting you to be able to completely and perfectly reproduce standard library functions because there's, you know, half a century of work that's gone into, you know, writing them, optimizing them, making sure that they work. But pretty much any programming task that's accomplished by a standard library, you should be able to write your own algorithm to do, right? The difference is, how much time do you have to work on the assignment, right? How much time do you have to debug all that code? Using the tools available to you is very, very, you know, useful. Anyway, I won't harp on it too much. I just, you know, don't be a that guy. Don't write 150 lines of code for the second question. And if you do, you know, try to do the format, this version afterwards to be able to compare to see how much work you did when you didn't have to. But anyway, same thing applies to this question. Anyway, so we will discuss the following types of features. This is only scratching the surface of what format tags are capable of. Rounding of floating point numbers and displaying a specified number of decimal places. Aligning columns of numbers, that is, dealing with white space in the form of the format tag itself. Right and left justification of outputs. Exponential formats for floating point numbers. Fixed field widths for various data types. One thing that I will note about this data conversion question that you have coming up, we expect you to produce output that is perfect to the character, right? Because the whole point is that you're using format tags to get it perfect to the character. Right? So, all of the format specifiers we are about to discuss are used in Printf and Scanf and all of their cousins, including Sn Printf and all the rest of them. Fprintf when we get to file I/O. So, format tags. You should know D already. Signed decimal integer. I, signed decimal integer, but does something different with scanf. O, unsigned octal. U, unsigned decimal. X, capital or non-capital, is unsigned hexadecimal integer. If you're working with signed hexadecimals, God help you. H, 1L or 2 L's, you place that before any integer conversion to indicate a short, long, or long, long integer respectively. These are called length modifiers. So, HD is a short integer, signed decimal integer, right? LLX would be a long, long unsigned hexadecimal integer. Make sense? Good. So far, so good. So, I think this works better if I hold up, do a side by side. So, various styles of printing, and they're what they will output respectively. Right? So, 455 as a decimal, regular decimal, you see it's fine. I and D are the same in Printf. Plus signs do not print, as you can see. Minus signs do, because of course, you know, this is like the positive, like a plus sign in front of an integer is basically like a null operation. It doesn't do anything at all. Printing as a short, we print a short value. Printing a long, notice the L here. So if you want to specify a literal, an integer literal, as having a particular size, there are suffixes that you can add to the integer literal itself that specifies its bit width. That's a useful thing to know. Printing an octal, it's 707. Printing unsigned doesn't print the sign, or does, wait, no, there's a mismatch here. Oh, no, I'm sorry, my bad. Printing unsigned 455, when it's positive, prints 455. Printing unsigned negative 455 prints this long bastard. Does anybody know why this happens? Yes?
It's just the highest integer minus 155.
Yes. What's that called? 2's complement arithmetic, right? So we're going to get into it a little bit more when we talk about bitwise next week, but essentially the way that negative numbers are represented in binary code is, again, you take the maximum value 111111111 and you subtract from that the the magnitude of whatever the negative number is, and that's essentially your representation. Fortunately, the math works. We're going to talk about it later, but just know that a negative number, when you print it as an unsigned number, will give you a very large number most of the time. Questions? No? Okay. There's a very good computer file video on it. if anybody wants to take a look at that. Just Google or go into YouTube, computer file, 2's complement, 15-minute video, and you'll understand the world. You'll understand everything. And then, of course, hexadecimal. Doesn't matter if it's capitalized or not. It prints in hexadecimal characters. That is to say, if you capitalize the X, it prints capitalized hexadecimal characters, but aside from that, like the actual value of the number is unchanged. It's just like a stylistic thing. So, good. So that's integers. Let's talk about floats. So we know f, which displays floating point values in fixed point notation. E displays in exponential notation. So this is roughly, well, not roughly. Essentially, this is scientific notation. So like 3.97 times 10 to the 8th gets printed 3.97E8. Right? You've probably seen this before, right? Yeah. 3.97E negative 8, of course, goes. You can have a sign character here, right? Sometimes they do it like E plus 0.7, stuff like that. There might be minor variations on it, but in general, that's how it works. If you use G, it will decide whether it uses F or E, depending on what the magnitude of the number is. If it's reasonable to express it in F notation, that is to say, if it's reasonably short, then it will use F. Otherwise, it will use E. Make sense? You put L before any floating point conversion to indicate that you want to convert a long double. So, again, size modifiers also work on floating point numbers. So, you can see we have these floating point numbers. Pluses don't print, minuses do, right? Capitalize the E, capitalize the E here. 6 digits to the right of the decimal point for F, like you're printing, here you go, and the default is to print 6 decimal places, right? And it'll just print the whole thing. And then G will, in this case, select E as its printing format because you have 1 billion here, so it makes sense. So far, so good? So, both E and F show 6 digits of precision by default, regardless as to how many are actually contained in the actual number. F will always print at least 1 digit to the far left of the decimal point. G will select E if the exponent would be greater than the specified precision, default 6, or less than -4, F otherwise. G does not print trailing zeros, F does. E and G display rounded values, F displays truncated values. So, you guys all know what truncation means at this point?
Just cuts it off.
Yeah, it just cuts it off. So, if you had, 1.329, if this were the point, under G, it would be 1.33, and under F, it would be 1.32. It doesn't round up. Make sense? Good. Oh, and you might want to actually print the percent sign character at some point. The way that you do that is you do a double percent sign. It's like how you get backslash by escaping backslash. So, This is important. Field widths. Have you ever been bummed out because it's getting C to print a table of values with properly aligned numbers is hard? Well, but right? Yeah, it's like, what are you going to do? Test the magnitude of every single number, insert the correct number of space characters? Well, guess what? C can do that for you. Inserting an integer value between the %sign character and the format specifier sets the field width. So, data will normally be right justified within this field. Field widths may be used for all format specifiers. If your field width is too narrow for your data will overhang the specified field width rather than being truncated. So, let's see some examples. I'm going to do the side-by-side thing again, just because I think that's easier. Ba-ba-boom. So, we're going to print out 1, 12, 1, 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, all at a field width of 4. That looks like this. So, up to the point where the size of the number is less than or equal to the specified field width, everything is right justified inside of that 4-character space. As soon as your number exceeds the specified width, it doesn't just chop it off, it allows an overhang. Right? This is true regardless it doesn't necessarily have to be the magnitude of the number that changes this. If the number is negative, it will require an extra character to print. So it begins its overhang with 3 numeric characters rather than 4. Or after 3 rather than 4. Does that make sense? This is a very efficient way to be able to gobble up white space, right? We're doing this in the context of printing things out, but if you switch your brain to doing this in the context of reading things in, let's, just have a random example. Let's say you were writing a program to be able to read the following dates. (12, 2012), 1, 2, 3. You wanted to write one program to read both of these dates correctly, right? Field width 2, field width 2, field width 4. Presuming these are space characters, right? And if you wanted to print something out that way, that's again the way that you would do it, right? Does that make sense? Good. We can specify various things for different data types using the .x format tag. This has different functions depending on what the underlying data type is. When you apply it to integers, leading zeros are included instead of spaces to fill the field width. So, for example, if that's not how you want to print something, but let's say you wanted to print that as 0, 1, 0, 2.20003, this would be 2.2, 2.2, 4.4. Right? I hope you're all paying attention because I'm basically giving the assignment away. We're recording, right?
Yes.
Yeah, okay, good. So, it will add leading zeros. When you apply this to floats, it controls the number of decimal places that are displayed, i.e. the precision of the number. So if you want to display a floating point to 2 places of precision, it's 0.2. If you want to display a floating point to 60 places of precision, then that's 0.6. And that, my friends, will give you whatever the floating point error of your system is, as was demonstrated in 1MD3 with the 0.1 plus 0.1 plus 0.1 example. How many people didn't take 1MD3 in this class? Okay, so when you guys have an opportunity, open up a Python interpreter, add 0.1 to itself 10 times, like 0.1 plus 0.1, etc., 10 times. See what you get as a result. It won't be 1. Oh, you know what? Fine, I'll do it. I'll just do it. I'll show you. I don't want to go too far off topic with this, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nope. You can see already though that
Yeah,
that's
plus minus.
there we go. You can see already from that though that we're getting things that are wrong. Would you like to know why this happens?
Sure.
So, you know how 1/3 you cannot represent it on a calculator? Like you just get 0.333333, right? It's the same effect, but essentially the problem is that not all binary numbers can be represented in the binary system with finite precision, right? So in the same way that 1/3 cannot be represented in the decimal system with finite precision, a number like 0.1 cannot be represented in the binary system with finite precision. So basically, that number gets cut off at some point. The way that we have agreed as a society to cut that off is after 52 binary digits. So you get 52 bits of precision to try to exactly represent this thing, and after that point it doesn't care. This is good enough most of the time. However, you can trick it in order to expose the error if you perform certain types of repeated operations. So you'll notice that this is very, 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 very close to 1. It's kind of a dramatic effect because 1 would be very short and this is a lot of digits, right? So it's a little bit facetious because the situation is not nearly as bad as it looks, right? But the moral of the story is that you should never, ever, 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 ever use exact equality comparison on floating point numbers. Because these types of errors lurk in the background. The computer, most of the time, will hide them. It'll be outside the range of the values that it will print, right? That's why if you, for example, format, hope I remember how to do this, as a .60f. Is this going to work? Yeah, there you go. 0.1 is actually this long bastard, right? Like, this is the internal numeric representation that's used by the computer. It's close enough to 1, or 0.1, that that won't matter for most calculations, right? But, if you take this, for example, right? Not even if I indicate it as a floating point number. 0.1 does not have finite like 1 has finite representation in binary because it's just 1, right? But this guy does, like this will not equate to the same as that, even though it should, according to our math brains, right? So, I'll show you the trick for dealing with that then. You don't do equality comparison. You subtract one from another. You take the absolute value of that, and then you check to see that that's less than some small number. So you're not checking to see that this, like, because equality is just going to go through each bit and check to make sure all of the bits are the same, right? What this does is it says, okay, give me this minus that, and so long as the result of that is sufficiently close to 0, I'm going to count it as a 0, right? Does that make sense?
Yeah.
Yeah. Question?
That seems like an optimization nightmare. That's so many more steps.
I mean, float, like, the attitude that has been taken towards all of this for quite some time is that if you're using floating point, you don't care about speed anyway. And this is kind of true for historical reasons, because it used to be that, like, you know, back in the day when integers were only 8 bits, floating points were still 32 bits. And so it would take, you know, a large number of clock cycles to perform a floating point operation on an 8-bit machine. So use of floating point numbers, period, was uncommon and only as needed, only as necessary. Like you can kind of see this as like you know, I think the best way to think of it, the best way to see this is in video game consoles. Like basically, if you take Nintendo games, floating point numbers aren't really used until you start hitting the N64. And because you're now like plotting in 3-dimensional space, you need to use floating point arithmetic, right? It's no longer sufficient to use integer arithmetic because you're trying to do, like, you know, space, right? But yeah, if you particularly if you look at like something in the Nintendo level or even Atari, like not a floating point number to be found. Yeah, it turned out that like the way that this was solved historically is that you would have floating point coprocessors that were sort of, you know, ancillary around the CPU, not necessarily integrated into the CPU itself, that were meant to accelerate floating point operations. And at one point in the mid-90s, one of the metrics for performance for a computing system was flops, or floating point operations per second. And you would like brag about how many megaflops your system was, right? Or gigaflops even. But yeah, no, floating point, like generally speaking, you're not really worried too much about optimization when you're using floating point. You're worried more about precision, if that makes sense. Question?
So, like you mentioned, like up until the N64, there wasn't really any floating point numbers to be found, like maybe because of like 3D environments. But like, what does that mean for like the Super Nintendo games, like was it Star Fox that was technically 3D?
Yeah. Notice how janky Star Fox is, though?
Yeah, fair enough.
Like, integers are discretized, right? Also, like, the N64 was 16-bit math, right? So you've got, like, a much, much higher granularity versus the Nintendo Entertainment System for the numbers that can be represented, but they're still like discrete, so you kind of jump between smaller positions, right? Whereas with the N64, you can actually have like 1.374825 as a position, right? And it's more continuous. Does that make sense? Yeah, cool. Another, yeah, I know, right? Another way that you can really tell is through audio codecs. But anyway. So, let's see if we can blast through this. So, when applied to strings, this sets the number of characters to display. The rest of the string will be truncated. Incidentally, if you're writing a string into a string using the string formatting tag, if that string is not null terminated, this produces a segfault, just so you know. %S instead of %C by mistake can also cause this. If you mean to print a character, print a character. Specifying a field width is an effective countermeasure against non-null terminated strings. So if you have specified a field width for the string, it will not likely encounter a segfault, though you will probably still get garbage data. So, going to skip that. Just have to skip the example. Sorry about that, guys. So, in addition, there are a number of flags that may be included to modify print format. So, minus left justifies, plus adds a plus sign preceding positive values and a minus sign preceding negative values. That's like accounting mode, where like you want to see the plus signs. A space prints a space before a positive value, not printed with the plus flag, etc., etc. Read that on your own. We've got to keep moving. So, file I/O. File I/O works pretty much the same as it does in Python, except you're passing pointers around. So we have the following essential operations: fopen, fclose, fscanf, fread, fwrite, fprintf, and feof. Feof. Using these files requires knowledge of the file structure, which is defined in stdio.h. We're going to talk about structures later. Basically, think of this as a kind of like an object which contains all of the information relative to the file that's currently being read, like what line you're on, where the file is located, what mode you had to open in. It will probably make more sense when we cover structs next week. This section assumes you at least vaguely recall how to do this in Python. So, fopen for business. Opening a file stream requires invocation of fopen. Fopen returns a pointer to a file structure. This is roughly equivalent to the file handle in Python. As you may expect, file name is a string containing the name of the file to be opened. The file may be specified by either absolute or relative addressing in the Linux sense, or Unix sense. Mode is a string specifying, among other things, whether the file will be in read or write mode. The output of this function is a file pointer to the data stream object. You do not have to worry about direct manipulation of this pointer. It is only interacted with via the file operations. Basically, it's a file handle. You save it to a variable. You provide it anytime you use any of these f functions. Right? Any questions? Other than that, it works pretty much exactly the same as open in Python. Here are your modes. R for read, W for write, A for append. Don't worry about the rest. In fact, you probably don't have to worry about appending. Fclose. Just as dynamically allocated pointers need to be freed when they're no longer needed, file streams must be closed when you're finished with them. It's an obligation to the operating system, and you don't want to make the operating system mad at you. So, fclose file stream returns 0 on success and an end of file code on failure. it just closes the file stream. It releases control of the file back to the operating system, where that control may be given to other programs. Fscanf. If you want to treat your file like you're reading information from standard input, then you can use Fscanf and Fprintf. So Scanf and Printf both have versions of themselves which operate on files rather than standard input and standard output. The only difference is that you specify file stream as the first argument. Other than that, it's exactly the same as scanf, right? So this would be a way of reading one line at a time. Basically, if you want like a mental picture for what's going on here, it would be like if a user were sitting down, entering the contents of the file one line at a time and pressing enter, and that was being read by scanf. That's what this guy does. Make sense? Sort of? A little bit? Okay. So, while the first argument is the file stream we are reading from, the rest of the arguments are used exactly like scanf. The return value is the number of input items successfully matched and assigned. That is to say, you have a format specifier here, right? You're presumably reading in a bunch of values and storing them in variables in the same way that we use scanf regularly. The number of those that are successful is the return value. Okay? So, if you're getting a number other than the one you expect, there was a problem. Fprintf, again, works very similar. In fact, it is easier to use than Sn_printf because it has one fewer argument and requires fewer pointer nonsense. So, Fprintf writes characters into a file in exactly the manner that you would expect. It just writes them, right? The first argument is the file stream. It returns the number of characters written if successful and a negative number upon failure. So, good. So one might ask, why would Fprintf fail? Any ideas? Yes?
If the file was like open for another program or something and it couldn't access the file.
Yes, if there's a problem with the file stream, it may fail to do this. Another example is if you're trying to write in read mode. Right? Question?
So like, is Fprintf and Fscanf sort of similar to like the less than and greater than in Bash, when we were like inputting files to grab arguments and like outputting two files rather than having it display on the screen?
Very similar, yeah. A little bit more formal, right? But yes, in general, like if you're directing a file to stdin and you're looping, like if you have a scanf loop that's looping through and reading all of that contents, that loop can be rewritten just by putting an F in front of the function name and like copying and pasting that loop into a place where the the file handle exists, and it's like one-to-one functionality by design. Make sense?
Yep.
Cool. Any other questions? Yes.
So similar to that, if you like Fprintf a file that already has stuff in it, will it overwrite it? Will it overwrite the amount that you are printing into it? Will it add it to the end? How will that work?
Opening a file in read mode, like regular read mode, overwrites the entire contents of the file. If you want to add to the end of the file rather than overwrite, you use append a mode. And I think there was like, R plus might do something like that, update instead of overwrite, but again, it doesn't really come up very much in this course. So, fread. If repeatedly invoking scanf isn't your style, perhaps you'd prefer writing chunks of file directly into memory as arrays. Size t fread takes a void pointer, a size, a number of memory bytes, and a file stream. All right? So pointer is a pointer to the memory block you're writing to. It needs to be at least as big as size times the number of memory bytes you're reading. So this function is agnostic about what the data format is of the file, right? So this can be used to read character data. If you're reading character data, this should be a character pointer, right? And size needs to be the size in bytes of each element that you want to read, so this would be size of character, size of char. If you're wanting to read it in as integers, right, this would be an integer pointer, or this would be a pointer to an integer array, this would be size of int, right? If you wanted to read floats, etc., etc. Most of the time it'll be characters, because it's rare, one of our Unix/Linux design things is that we want to keep files in plain text, character encoding as much as possible. So this is going to be characters most of the time, but binary data might be different, you have the ability. NMB is the number of elements to read each the size of size. So this is like the cap on the number of bytes that you want to read from the file, which is good. Stream is, of course, the file stream, and fread returns the total number of elements successfully read. So it'll just read everything, block it in, dump it into memory, and then you can work on it from there. It's your choice which one of those you prefer. There's some pretty terrible puns in this. In reverse, fwrite. Pointer, PTR, is a pointer to the array of elements to be written. Size is the size in bytes of each element of pointer. NMB is the number of elements to be written. Stream is obviously our old friend, the file stream. And the return value is the total number of elements successfully written to the file stream. So the exact same process in reverse, right? You can dump directly from an array into the file stream. However, if it's not character encoded in your C program, it will not be character encoded in the file. So, FEOF. FEOF is a function that tests to see if the file stream has reached the end of the file. EOF. In Unix, files include an end of file character, which, in the same way that null termination tells you when a string is finished, the end of file character tells you when the file is finished. It's an ASCII code. So, FEOF tests to see if the file stream has reached the end of the file. Input is the file stream, naturally. Output is non-zero if the end of the file has been reached, 0 otherwise. Right? Now, it looks like we may not have time to, Are you guys okay with this class going like 3 minutes over so that we can do the example of file I/O? This is the last thing we have to cover today.
No. Okay, go ahead.
Well, I wanted to check because, I don't know if you guys have like anything going on or anything, Maybe there's a big party I wasn't invited to.
I'd always invite you to the party, you know that, right?
Do I know that? Do I know that? I'm kidding, of course. Right. So let's build this up from scratch then, since I have your permission. Get it fileio.c. So we will, of course, require standard I/O. I guess, I don't think that ever actually appeared in the slides that all of these functions are contained in stdio, but I guess I didn't want to insult your intelligence by assuming that you wouldn't be able to figure that one out, because, you know, it's called standard IO. So, you know. Int main. So let's create a file pointer file handle and fopen. What do we got in this folder? Sure, that'll do. Clients.text in read mode. Cool. So now let's just do it the easy way. Character array contents contains 1,000 characters. Freed contents. The number of elements that we want. Oh, the size of the elements is we want to do size of character. The number of elements that we can read is 999. Null termination. And then the file handle will be the last element there. And in theory, printf should be able to print this string relatively easily. Let's see if this is, let's see how far off base I am here. GCC, W all, file io.c. Ah, it compiles. A.out. There you go. File contents read. Boom. Including things like new line characters. Right? So, let's say that you wanted to perform some small manipulation of this file, right? So let's say, for example, you wanted to replace every letter O with a question mark or something. So for int I is equal to 0, I is less than 1,000, I plus plus, if contents at I is equal to capital or lowercase o, then contents at I is equal to question mark. Then we print the contents. Oh, perhaps I should remember my semicolons. There we go. You can see that this is just a character array in the regular sense of the word. Now, oh, and I should probably I should practice what I preach, eh? Close file handle. Then, rather than printing here, we can fprintf to a new file Actually, I can reuse the old handle. Which is equal to f open. Let's say clients.text.out in write mode. And f close, fh save. How am I doing? I've got warnings.
Your F-
Oh yeah, I've got to include the file handle, don't I? There we go. Thank you. There we go. Warnings unwarninged. There we go. Nothing is output. But we do have clients.text.out. And if we take a sneaky peek inside, you can see that this is the updated version of the file. Any questions? Personally, I find fread easier to use than fscanf because you can do it all without the loop. And when you're using fscanf, the terminating condition for the loop is you're testing feof, right? So, yeah. Any questions? All right, I guess we'll adjourn for today. Oh,
Sorry, can you move to that other window because I'm like copying the code down?
Oh, yeah, sure. Yeah, I'll leave that up for a bit. Okay. Good. I know I make it look easy, but it takes practice. So, yeah, good. Good luck on the lab today.